Hello, everybody, and welcome to another episode of Analytics Mindset. This is going to be the linear regression with Excel video. And originally, I was just going to walk you through one way to go through Excel and understand some of the output of linear regression. However, I'm actually going to do something different. We will start by viewing at different ways that you can get linear regression in Excel and add it to this Excel file here, to this Excel workbook, because even though we have done a lot of stuff in the past and a lot of it is very programming heavy, I do feel that sometimes you just need to use the easiest tool at your advantage or the most common one. 9 times out of 10, that is going to be Excel. Why? Excel is everywhere. You can use it for a lot of things. And probably the most important one, a lot of people understand Excel. I am not diminishing the importance of all the tools that we have learned before. We have done linear regression in Python, in fact, already, and I have like 3 videos on that. I will leave a link somewhere here if you want to revisit some of my videos. Those are some of my earliest videos, but it is good to double check if you want it. There is going to be quite a little bit of overlap here, mostly because the concept of linear regression is the same. It really doesn't matter where you do it. My point is you need to have the proper tool to do the proper thing on the proper time. And Excel is just easy to do in a lot of things, and it can be very powerful depending on how you leverage it. Without further ado, we are going to start with linear regression in Excel. There is actually a couple of ways that you can do Excel to perform linear regression. If you're like me and you went to have a stats class, maybe it was called statistics 1, maybe it was called business analytics, maybe it was called something else, you may be familiar to this first one. For this first one, it's actually the trickiest one because it's not available in base Excel. You are going to need to go to the data ribbon. So assuming that you start with this and you can see I have my data here, it is very, very simple. You can just take this, I'm gonna make it a little bit bigger, but you can just take this into your own spreadsheet. You don't need to download any files like with my other GitHub code that I have developed or do anything else. You plug and play and you are able to just take this very small data set that I just made up. But to start with, you are going to need to go first to File, and then you're going to need to go to Options. Here, you go to Add-ins and Manage Excel Add-ins. You should see Analysis Toolpak here, and that is the one that we're going to look at. Toolpak allows you to perform a lot of stuff, not only linear regression, it is a very handy extension to have in. By default, you're most likely going to have it like this. You want to click it with Toolpak and click OK. When you do that, you can go to the Data tab now in Excel, and you should have this Data Analysis option. Now, we are going to click on it, and then you can see we have covariance, descriptive statistics, F-test, for analysis, histogram, moving average, and a lot of other stuff. We're going to go with regression. It calls it regression. It is standard, simple, least square linear regression. That will be the best term to say. And we will go through very little on what actually least squares means. I already went a little bit in detail in my other videos, but I will go in this video just in case because I want to also make it self-contained. And that's why we have season 2 of Analytics Mindset after all. You need two variables for linear regression. You have a y variable and an x variable. If you're not really that familiar with linear regression, you are establishing a relationship between an x or independent variable if you come from the more machine learning side of this of the school of thought, and a y or dependent variable. You are establishing this variable is connected to this variable, and this is how they are connected. We are going to start with our y input range. I'm going to take this column 2. I'm going to do something very similar with my x range. I'm just going to take this. And notice how this tool particularly allows us a lot of flexibility. Labels, that's something that it's always appreciated in Excel because sometimes you just want labels. I won't include the labels in this case, yes, because I'm recording this live and I don't want Excel to do funny stuff, but you can just do that. Confidence level is something we are not going to touch right now, but you can actually set that up by yourself. By default, it's 95%. Is to perform some hypothesis testing that in the nature of linear regression, you're always going to do that because you want to know if the coefficient and each of the variables are, in fact, the relationships are significant or not. They will perform that at a 99%, 95% confidence interval. We are not going to get the residuals or the plots or the line fit plots, and we are not going to get this normal probability plot. Very plain, very basic linear regression, no very different from what we have done back in Python when from scikit-learn. We just called linear regression and perform that. I'm going to do this. And here you can see Excel actually gives you a lot of information that is not in Python when you perform linear regression. Why? sklearn is a data science slash more inference focused tool. It's a package that was developed for AI and machine learning and all that stuff. This is more classical linear regression. We are here more focused not that much in prediction, although we can do that, but on statistical inference. That is one of my favorite parts actually of statistics and linear regression. You can see here how we have multiple statistics here. The multiple R square is how well the line is fitting the points in the regression line. You have the multiple R, the R square here. The R square is that one. It's just it's just that, and then you have the adjusted R square that adjusts for the number of variables, even though we only have two, the standard error and the observations. There is only 4 observations. That's just a count, not really anything out. It performs a node analysis for you. If you wanted to do that, guess what? You can just do a regression analysis and get that as well. Most importantly, we have an intercept and an X variable. What does this mean? We basically fitted a line in a plot between the observations and said, this is the intercept. When the value of y is 0, this is where we need to add it. So our line actually crosses the x-axis. And this is the y. This is the actual, in the variable 1, the relationship between the two of them. For as much of a change in the x variable, this is how much the y variable is going to change. You can actually calculate this if you wanted to, and we will do that in a bit. Not with this, because I like this output, and it's very nicely formatted for you, but we will calculate that later. Just remember for now that the intercept is 2.36, more or less, and the relationship between x and y is 4.14, meaning that for every 1 that x increases, you can expect y to increase by 4.14, and that makes sense given our observations. But as you can see, you also get your t statistic that I won't go that much into detail here because it's a little bit of a more advanced statistic, but basically it's calculating, given everything, how far away is it of what we would expect it to be random. And then you have the p-value that basically means, is this significant or not? Is this, can we say that this is actually, we can reject the null hypothesis that in the machine to detail, I keep saying that you are saying, I can say with this confidence interval 95% in this case, because we decided that this is not equal to 0, that this intercept or this coefficient, that's the actual formal name, is not the same as 0. You have your upper and lower bounds. Yeah, that's pretty much it. That is linear regression Excel. Now, if you are not really that familiar with linear regression, this does not mean a lot to you. We are going to go ahead, come back to sheet 1. We're going to rename this data, yes, because we can. And we're going to rename this out back to data. There is two more ways that I know of. There probably are hundreds of ways. And if you install different packages in Excel, probably each of them adds their own stuff, the add-ins. If you download a custom add-in, may add additional ways to do it. The other two ways more commonly that I found in Excel is with a very handy way. You're going to take column 1 and column 2. And then you go to insert, and this does not require the analysis toolpak that we just actually enabled. You're going to go with scatter. When you have the scatter plot, you are then going to come here and add a trend line. And if you go into more details in the trend line, you can see you can make linear, exponential, forecast, or to period moving average, where you just go with linear, more options. And we are both gonna put display equation on chart and R squared. You can see how you can actually fit a lot of functions, and there is a whole world of linear models out there. That's a very in-depth topic. This is basic, classical, simple linear regression, the most basic model you can have. If you get this, it's probably going to make your life easier, because even the most complex neural network is not doing something that is very different from this. It's a very overcomplicated way to say you have these predictors, independent slash X variables, that are predicting this, the outcome, the actual Y variable, dependent variable. You're establishing a relationship between the two of them. And that's what makes linear regression so beautiful. It is the simplest way to do it. This is what I mean by these squares. You are taking, it's actually just a linear, the actual this squares formula is not that complicated, and you can derive it. And if you have taken a calculus class, you definitely have seen it before. But you are just calculating both a coefficient and an intercept, and then fitting the baseline that will reduce the least square, the error slash difference of each point square. Because if you just do it one, it's going to cancel out the negatives and positives. So we want them square. There is other ways to do it, but least squares is the simplest algorithm. As you can see, it fits this line pretty well. There is only two of them. This is a little bit up, yes. This one is also a little bit up. But check out the formula for a second. You have here your Y, that is your outcome. So you can actually use this formula to predict where the next one is going to be, and we will do that very soon. But check out the R squared too, 0.99. Now let's go back to the output. And you can see here that the intercept is almost exactly the same, but given random errors. The intercept and the coefficient are almost the same. Why is that? Simple. It is using exactly the same algorithm. It might be a different implementation. If you put this in Python though and call the linear regression in sklearn, you are going to get exactly the same line. That's the beauty of these more defined models that do not vary with new data, with the data. For this specific data set, for these 4 observations, I can say with confidence, this is the best simple linear regression line using the least square algorithm. And there is a lot of beauty in that statement. But you have found the best line that fits these 4 observations using the square value of the errors of each of them. That is beautiful, at least for me. But it is something that can help you understand your data way more, and visually, you can appreciate it a lot more here in this graph. than just looking at all this output. But yes, this output gives you a lot more detail, but it's not really intuitive unless you're familiar with it. That's option number two. There is one more way that we will use very handy to calculate the predictions. We're going to call these predictions. In R, you will usually call it pred. Everything is called pred because you're predicting everything. I will just go with predictions to not make anybody confused along the way. There is one function, Linest. Linest stands for line estimation. Return statistics that describe a linear trend. We have a linear trend here, matching known data points by fitting a straight line using the least squares method. Yes, exactly what we have done. This is the last implementation in Excel that I know of. Again, if you find any other implementation in Excel, let me know. And I will gladly either add it in my description to say, hey guys, I missed this, or something else. But you can just use Linest. And in this case, you're going to bring your know whys. When we were doing the data analysis toolpak, we first put X and then Y. In this case, we're putting Y first. Our Y is column 2. Our X is going to be column 1. We are going to let both the constant and the stats to the default values because we can do a lot of other things. But by just bringing those two up, we are generalizing to the simple linear regression least square algorithm. And not confuse myself, I'm going to refer back to my formula over there. That's the coefficient. And this is the intercept. Notice how, yes, there is a rounding error, but probably there are different implementations of the least square algorithm. Most likely, I mean, they are round up all the way to 7.1. Most likely, it's just a very rounding error, pretty much. Besides that, it's pretty much the same. But now we got our formula, and we got it here too. For each observation, we are going to calculate is the value of X times, because that's the coefficient, this, the coefficient, 4.14. And then we're going to add to that the intercept. Mind you, it's almost the same value here. That's why they are almost there at the same value. Probably there is a very small difference between, because the line goes there and the line actually goes all the way over here. So this is the 2 that it's talking about. But we are going to do exactly that with all of them. So we are going to add this to make sure that we can just scroll this down. And we are going to bring all of this down. How you calculate the absolute error? And the squared error. Is very similar, but you will see the difference here. This is going to be just apps, the function apps of the actual output, less its prediction. And we will do exactly the same for all of them. Here, we're going to take this less this, but we are going to square it instead. Now, for this regression, this is what matters, the square error. You can say, and there is other algorithms too, because least squares is just one of the other ones. But you can say that this line minimizes, that is a whole other topic. There is a lot of optimization going on there. But this line is the one that minimizes those square errors for this given data points in this regression line. You can say that with total confidence. Now, there is some additional stuff that I want to go through first before, as we have already calculated the absolute error and the squared error. You might ask me, what if we decide to just create a new one? Let's add a new data point. Maybe I have another observation. This is going to be 11, and this is going to be 55. What happens then? Well, we're going to do exactly what we did before. And I'm just going to go with our insert method so we can see what's happening. We are going to create a scatter plot with our new one. And here we're going to add our trend line. And we're going to display both the equation chart and this. Uh-oh, it's different. Why is that? Because the line has shifted. Now, as you can see before, the line, when we had 4 observations only, went below the third observation. It was a little bit below there, but because the new observation is bigger here and it has another error, we need to rebalance our line and basically tilt it this way. We are tilting that line in order to fit it. The line that was the best for those 4 observations is not the same for these 5 observations. That is something that you need to be very careful when somebody asks you. We have this regression line. Is it the best if I add this observation? The answer is no, most likely, unless you actually exactly match where the regression line is going. So one of the outputs of the predictions that is very unlikely, if you add new observations, the regression line will change. And we actually can do exactly the same we did before. We're going to do line estimation. And we're going to take our y's and our x. And you can see our intercept is now negative and our coefficient increased. The line is now tilted more this way. Instead of being flatter, now it's going up a little bit faster, but we have moved the intercept down. And if you have seen linear equations and things like that, or more advanced calculus, you can probably tie back a lot of this from the very brief explanations I'm giving. But this is standard for everybody, this video. Therefore, I'm not going to go that much into detail there. Just know that there is a ton of very advanced math hidden inside this very seemingly simple algorithm. You created a new regression. Therefore, we need to calculate news. And we're just going to go with the squared errors. We are not going to repeat the absolute errors just for the sake of time. And we need to create a new set of predictions. We're going to take this, and then we're going to multiply it by coefficient and then add our intercept. But we are not using the old ones anymore. We need to use the new ones. And I will just go ahead and fix these two so we don't have issues when we're moving it down. But see, my predictions are different now. Now, if I take this less this, and then I square it up, you can see that my squared errors are different. They are actually higher. That's my main reason why my R squared went down. I won't go that much into detail about R squared and correlation, but basically higher correlation, higher fit, higher R squared. Everything is better for the algorithm. Notice how the squared error for the last observation it's way lower than the original R squared and the original squared error calculation. That's no accident. It's a trade-off that the algorithm did. Now, you're not fitting as well the other observations. As you can see, the first two had higher squared errors, even though by very little. The third one passes right through it, actually better than the original one, so the squared error actually went down. The fourth one has a very big square error, but it's because it's compensating for the last one. It's giving the line the flexibility to change a little bit in order to reduce that last point. That's the outlier. If we were talking on more on these terms, you need to fit it, and therefore that's why the error is high. There is a lot more in linear regression. It is a very simple, seemingly simple algorithm, but by this way, I want you to be able to do it in Excel through different ways if you need to explain it. Now you know that baseline is the best for that data. If you get a new set of observations and you need to do another one, you are going to need to recalculate that. Excel makes it very easily. You saw it. I was able to do it in three different ways in less than whatever long this video is at this point. And with that, I just want to close this by saying these algorithms can get so fascinating. You have this static line that changes based on the observations, but sometimes the relationship is not quite linear. You can make a logarithmic line, exponential line, spline. You can actually try to fit the data as much as you want. You can use polynomials to feed you data at the first, second, third, fourth degree. A lot of the more advanced models are nothing more than that. You are just adding on top of linear regression and making the linear model family is very extensive. And this helps a lot with understanding. Is think it as a gate. If you really understand linear regression, if you can do it in Excel, you can do it in Python, you can do it in R. You just need to know what arguments to put in the programming language. It is just a placeholder there. Even Tableau can do linear regression now. Um, the concept is the same, but the beauty behind it is still the same. The algorithm that creates it is still the same. You just need to know how to create it and when it's appropriate and when it's not. If your data does not look linear, that's why it's always good to actually plot your data. You should not use linear regression or any linear model that does not take that into account, to be honest. You should always use linear regression when you seem to find a linear relationship. Like in this data, I created this data. I actually, just in my head calculated, well, this goes from 2 to 3, this goes to 10 to 15, and then 24 is a little bit off, and then 35, and then 55. But it is still very close to perfectly linear. And I will let you as an extra credit assignment. Think of a perfect linear relationship. What would that equation look like if you had a perfect linear relationship? Give it a try. Is there one answer? Is there multiple answers? Yeah. All right, I do hope that this video finds you well, and I know I have been a little bit behind on my release schedule, but things happen. I will do my best to keep pushing the last episodes of Season 2 of Analytics Mindset, and as always, if you have any comments, please let me know, any kind of feedback, and I hope you have a great day. Thank you.